this video we're going to look at concavity, in particular the second derivative, because that's what measures the concavity of a function. So if the second derivative is positive, that tells us that the first derivative increases. And that's the same as the first derivative. When it was positive, it told us the original function f of x increases. So we just have to use the same form of reasoning, or a line of reasoning. We just have to kind of move it along one more derivative. So the second derivative is keeping track of whether the first derivative is increasing or decreasing. So as I said, if the second derivative is positive, first derivative increases. And what exactly does that tell us? Well, it means the tangent slopes are getting bigger, more and more positive, or they are increasing. And if that happens, you will see the tangent lines sitting below the function. And we say the function is concave up. So here's a visualization of that. If you look at these red tangent lines, they are all getting more and more positive. And they're all sitting below the function. So that function is concave up. And I should note that the middle tangent line is a stationary point here, and also a turning point. That doesn't necessarily have to happen, but we'll get into that in a little more detail later in this video. Okay, now if the second derivative is negative, that tells you that your first derivative is getting smaller and decreasing, so your tangent slopes are decreasing, meaning more and more negative. So the tangent lines will now sit on top of the function, and we say the function is concave down. And here's a visualization of that, with tangent lines getting more and more negative, sitting on top of the function, and that's the visualization of concave down. And again, we have a stationary point in the middle there that doesn't necessarily have to happen, but is always also pretty common to happening as well. Okay, and to help you memorize concave up and concave down, you know, if you're feeling up, you're smiling. If you're feeling down, you're probably frowning. If we add some googly eyes to that, well, it makes everything better when you add googly eyes, but most importantly, if you add googly eyes to the left-hand diagram here, you will see all of those tangent lines are underneath your curve. So if your curve is smiling, it's concave up. If your curve is frowning, the tangent lines are now sitting on top of your function, and your curve is concave down. One other item we have to deal with concavity is an inflection point. A function has an inflection point at x equals c if and only if the second derivative is 0 or the second derivative is undefined. And of course, that's probably causing you to flash back to critical values of your first derivative. But please don't call these x values critical values. That only applies to our first derivative. We're just going to keep track of these x values and call them possible inflection points. So if you're wondering how the second derivative can be undefined, well, there's a couple of ways. You could have a vertical tangent there. You may have a sharp point or cusp there. And also, I guess you could have a discontinuity. You might have a vertical asymptote or some kind of a jump discontinuity or the like. But keep in mind, if we have an inflection point there, we have to rule out discontinuities. So your function, the original function, has to be defined at x equals c. So the only thing we really need to worry about if we get into the more unusual second derivative being undefined is basically consider the possibility of a vertical tangent or a sharp point there. There's an important and here, which brings us really to the true definition of an inflection point. An inflection point is a location in a function where the concavity changes. So once you recognize an x value makes your second derivative 0 or undefined, that's not enough until you confirm that your concavity is changing on either side of that x value. So, of course, changing concavity means it's going from concave up, smiley face, to concave down, frowny face, or vice versa. And one last, I guess, feature of an inflection point, if you have a true inflection point for a function, you will see the tangent line cutting through the curve at that exact point of tangency. And here's an illustration of that as well. This is a cubic polynomial that we will actually look at in detail in this video in a few more moments. And this cubic polynomial, as you can see, has an inflection point right at the origin. The tangent line slices right through that function. Right at that point of tangency. And if you look to the left of that inflection point, you will see a smiley-faced function, a concave up function, and to the right of that inflection point of the origin, you will see a concave down frowning function. So the concavity is definitely changing, and I make that even, I guess, more obvious, you can also recognize that your tangent line is slicing your curve at that ordered pair as well. That is an inflection point. So it's great to be able to, I guess, recognize concavity when you can see it on a graph paper or a graphing software, but it's not everything that we need to be able to do. Of course, we need to be able to analyze concavity using pencil and paper. So for the rest of this video, we're going to take some time and analyze this exact cubic polynomial that you're looking at right there and figure out how we can do a little work with the second derivative and identify, I guess, where the function is concave up and down, and possibly most importantly recognize that this function also has an inflection point where it changes concavity at the origin. Okay, so now let's look at that cubic polynomial we just witnessed moments ago. We're going to now analyze it. Good old pencil and paper method, I guess, where we're going to look at the second derivative and use it to determine the intervals where the function is concave up or down and determine the exact coordinates of every inflection point. So as soon as you see concavity and inflection points mentioned, hopefully you recognize right away that you need your second derivative. So to get that, we need to first go through our first derivative. So if we differentiate x minus x cubed, that'll be 1 minus 3x squared via our power rule, of course. And then to get our second derivative, we'll differentiate the first, and we'll differentiate 1 to get 0, and bypass the minus 3 and differentiate x squared to get 2x. So of course our second derivative will be negative x 6x. So of course we can just write that. And now we consider possible inflection points. I'll just say IPs. So possible inflection points, remember, is whatever x value can make your second derivative 0, which by looking at minus 6x, x equals 0. It's the only x value that'll make negative 6 times x 0, just by inspecting that. And consider the possibility of an undefined second derivative, which of course can't happen for a polynomial function. So nothing weird in this first example, just relatively straightforward. 1x value, that's a possible location of an inflection point. And of course it just simply made our second derivative equal to 0. So now we'll do a sign diagram for our second derivative. We'll label that. Especially if you're getting more than one sign diagram in a problem. If you actually are working with the first and second derivative, I think it's a good idea to label your sign diagram. So our possible inflection point, remember, do not call that a critical value, even though technically I guess it's a critical value for the second derivative, but we usually only use the term critical value for the first derivative. So if we look to the left of 0 and we plug in something to the left of 0 inside our second derivative or into our second derivative, like negative 1, we'll recognize that's going to be negative 6 times negative 1, or positive number. So our second derivative is positive to the left of 0. And similarly, if we look to the right of 0, plug in 1, it does the trick. We'll get negative 6 times 1, so our second derivative is negative to the right of 0. So that means our tangent slopes are increasing to the left of 0, and then they are decreasing to the right of 0. And just to recap what we mean by increasing tangent slopes, remember, if your tangent slopes are getting more and more positive, think of something negative and less negative, maybe even 0 at some point, but that's not always a guarantee. And then of course more and more positive. Those are increasing tangent slopes, and you can see that that definitely traces out a concave up section of your graph or for your function. So that would mean if we see positive signs above our second derivative, our tangent slopes are increasing, and we have a concave up section of our graph, a smiley face. And on the other side of 0, using that logic again, if we have tangent slopes getting more and more negative, we can start off with a positive tangent slope, less positive, maybe 0, which it is in this function, but it's not always a guarantee, and then more and more negative. If we see something such as that, then of course that's a frowny face, that's concave down, and that's what happens when your tangent slopes are decreasing. So we can label that as, in terms of concavity, as concave down to the right of 0. So I don't think you need to really analyze your tangent slopes too much anymore. Just get in the habit. I mean, take a few moments to do that so you understand what the second derivative is measuring. But once you do that, positive signs, second derivative, concave up. Positive is happy, smiley. Negative signs over your second derivative, sign diagram or number line. That's you're down, you're frowning. Of course, that's concave down. So let's finish off. All we got to do now is write down our intervals, which to me is already done on that sign diagram, honestly, but just in case somebody asks you for intervals, I guess we really should write them out, which is a bit of a nuisance, especially since we have a decent sign diagram there. But let's do it, and then don't forget we have to write down the exact coordinates of that inflection point as well. And by the way, this is an inflection point because I think it's pretty obvious our concavity is changing. So we can say f of x is concave. From left to right again here. It's going to be concave up first. And that's over the interval x belongs to negative infinity all the way up to, but not including 0. And then f of x is concave down. And that's going to be over the interval x belongs to 0 to positive infinity. And that change in concavity allows us to also to conclude, as I just said, that f of x has a inflection point, or an inflection point, when x is 0. And you can write IP here, but I think I'll write out inflection point in the summary. An inflection point at x equals 0. We'll write the coordinates because that's what we were asked for. And if we plug 0 into our function, I think you can probably remember our function's x minus x cubed, so plugging 0 in there gives you nothing but 0. 0 minus 0 cubed, so of course our ordered pair y value is going to be 0 here as well. And that confirms that this function, of course, has an inflection point at the origin. So nothing terribly complicated with the polynomial. That's why it's a good place to start. Once you get your second derivative, figure out what makes it 0 or undefined, which wasn't a possibility here for a polynomial. And once you get those possible IPX values, do your number line test, just like you did back when you were analyzing your critical values in your first derivative. But now this time, positive signs mean concave up and negative signs mean concave down. And list your intervals to describe your concavity. I guess summarize your concavity, and then if you see changing concavity, you have an inflection point. And let's take a few minutes as we wrap up this video as well. We'll go to Desmos quickly, and we'll just kind of analyze our behavior of our tangent slopes to see how it's, if we understand how our tangent slopes are increasing and decreasing, then we really understand and can measure the concavity of this or any function. Okay, here we are to, I guess, have one last look at this cubic polynomial function, x minus x cubed, and I already have a tangent line on the curve. At a point of tangency, it looks like x equals -1, that x-intercept, actually. But let's get to the concavity part of this function, which is what we're worried about right now. Notice all these tangent lines have negative slope, but the tangent slope seems to be getting more and more positive. And you should also note that the tangent lines are underneath the curve throughout this entire section of the graph up until, of course, it hits the origin, somewhere about there. Now that's where our concavity changes, and the tangent line right now is slicing that function right at its point of tangency at 0 and 0. And then after we keep moving to the right, the tangent lines now sit on top of the function. And the tangent slope is getting more and more and more negative now. And that's, of course, a way of detecting, I guess, a concave down section of our graph. So one more time through that, notice all those tangents are underneath the curve. They're getting more and more positive. So that's a concave up section of our function, or interval of our function to the left of 0. And notice the smiley faced function there, concave up. And then as the tangent lines get more and more and more negative, they sit on top of the function, and that's the frowny section of our function, the concave down interval, I guess, of this function as x is greater than 0. And note the function, tangent line rather, does slice that function right at the origin, which is further evidence that we're dealing with an inflection point. But I think the most important evidence of an inflection point is that change in concavity, and that's really all I guess you should be looking for. So there it is. we rounded out our introduction, I guess, to concavity, and we started off with a pretty safe example. But again, if you can understand everything we've covered in this video, you should be good to deal with, I guess, some stranger examples coming up in future videos.